Hi, my name is Brian Caffo, and welcome to the Resampled Inference lecture as part of the Coursera Inference class, which is part of our data science specialization. This class is co-taught by my co-instructors Jeff Leake and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. So the Bootstrap is a tremendously important and useful tool for constructing confidence intervals and standard errors and basically performing inferences where it would otherwise be difficult. It was invented in 1979 by a famous statistician named Efron, who's in the Stanford Statistics Department, easily one of the top statisticians in history. And I would say the Bootstrap is one of the most important procedures that's been discovered in the history of statistics. And the reason being that it really liberated data analysts from having to do a lot of mathematics in order to perform inferences. So just as a simple example, if you wanted to do a confidence interval for the median, there are some kind of complicated asymptotics that you can appeal to, but it involves a lot of mathematics. On the other hand, you can just perform a bootstrap and it gives you a confidence interval for the median without having to do all of that work. So it, maybe dangerously so, but nonetheless, it liberated people from having to do a lot of complex mathematics to understand some distributional properties of statistics that they calculated. The phrase bootstrap comes from the name of the procedure bootstrap comes from the phrase pulling oneself up from their own bootstrap. That phrase, I initially thought it came from the Baron Munchausen character, which, by the way, if you haven't seen the Monty Python movie, you definitely should. I thought it came from that, but I've since read that it maybe even existed earlier than that. And the idea of pulling oneself up from one's own bootstrap is the idea of doing something that's physically impossible. And that's not a terribly appropriate name for what's going on in the statistical procedure, the bootstrap, because we can draw a direct line from the information that we're using to the inferences that we're making. So it's not at all like pulling oneself up from one's bootstrap. It's quite possible, and how it's working is pretty clear. So it's an important technique. It's very liberating. And I think it's also very much so in the spirit of data science. So consider this example. Imagine if we wanted to evaluate the behavior of the average of 50 die rolls. So our population distribution is this left-hand distribution, the equally weighted bars at the values 1 through 6. And there's a couple of ways we might go about doing that. One is we could just try and mathematically figure out what the distribution of the average of 50 die rolls is with no simulation, just doing the relevant algebraic calculations. Another way to do it would be to roll a die 50 times, get an average, and then repeat that process over and over and get lots of averages of 50 die rolls. But this is predicated on us knowing that the true population distribution is 1/6 at each number, right? But it does seem to be an easy way to do things, because it would be hard to sort of figure out exactly what's the probability of getting a 5.5, right? Instead, it's easier to just roll the dice 50 times, take the average, repeat that over and over again, and get a pretty good sense of it. Now, a lot of these things for the average we don't have to do because we know things about the distribution of the average. We know that it's centered at the population mean. We know that its variance is sigma squared over n. Several things like that. But I'm going to talk about it with respect to the average first, and then you'll see hopefully how this extends to other statistics other than the average. So let's consider a very similar problem. Imagine if you didn't know whether or not the die that was generating your data was fair. We didn't know that the probabilities it placed on 1, 2, 3, 4, 5, or 6. So what we have is one sample of size 50. So we only have one average, not a distribution of average, from whatever the die was that was generating the data. So here on the left-hand side, I'm showing you the histogram of the various occurrences 1, 2, 3, 4, 5, 6 for one sample realization that we drew from this population. Now I can't evaluate what's the behavior of averages of 50 die rolls from this population because I don't know what the population is. I don't know what die to roll from to execute the simulation exercise. So what bootstrapping says is, well, why don't we do the next best thing? Why don't we sample from our empirical distribution, repeatedly sample collections of 50 die rolls, not from the true distribution, but from whatever our sample of size 50 estimates. So in this case, I would sample from these blue bars with the heights, with the probabilities related to the heights, and I would do that over and over again, and I would get averages, repeated averages of 50 draws from this distribution, and that would tell me about the distribution of averages, even though I only get to observe one real true average from the real population. And that's the process of bootstrapping. Mechanically, what we're doing is taking each observation, each 1, 2, 3, 4, 5, or 6 that we get, and throwing them into a bag, and then drawing out samples of size 50 where we're drawing with replacement. So the same the same data point might get taken out twice in this process. Sampling from that bag, samples of size 50, taking the average, and repeating that process over and over again. But the fundamental idea is to exactly replicate our simulation experiment that we would have done if we could roll the true population die with the observed distribution generated by the specific one realization of 50 die rolls that we got. Okay? And so that's the basic bootstrap principle. We use our data, our observed data, to construct an estimated population distribution. We simulate from that population distribution to figure out the distribution of a statistic that we're interested in. And that's the basic idea. So we'll go through some examples now with less contrived settings than this die roll example. So let's consider the library using R and then the father.son data. And just to make my life a little bit easier, I'm going to define X here as the son's height, just so I don't have to keep referring to the data frame. Let's let N be the number of observations, and then I'm going to do 10,000 bootstrap resamples. So what I'm going to do now is the sample command. So when I say sample X, that means draw from X, N times B, numbers of resamples, where in every case, because I put replace equals true, every time I take an observation, I take a sun's height out of the bag, I put it back in. Okay? And so what is this? This is simulating from an empirical distribution defined by our data that puts probability 1 over n on each observed data point. This is called the empirical distribution. And then I'm going to arrange these in a matrix with number of bootstrap rows and number of sample sizes columns. And so what that means is every row of this matrix that I'm calling resamples is now a completely resampled data set where I took my original data and I drew a sample of size n with replacement from that data set. And that's exactly equivalent to regenerating a sample of size n from a distribution that places probability 1 over n on each observed data point. And then let's suppose that the statistic I'm interested in is the median. And so I'm going to take for each of these data sets, each of these resampled data sets, and I'm going to apply the median. And that's what this final apply statement does. So here's a density estimate from the resampled medians. I've drawn a vertical line for our observed median. So what we've done in this case is we've taken our vector of sun's heights and we've repeatedly drawn from this collection of sun's heights a new data set of the same length where we drew with replacement with equal probability on every observed data point. Then for each one of these new data sets, we calculated the median. We did that 10,000 times, and we got a collection of medians. What this density estimate is is an estimate of the distribution of medians where we don't know the actual population distribution. We're estimating it from our observed data. This is the central quantity used in bootstrapping. For example, in this case, we're bootstrapping the median, and we might want to do something like take the standard deviation of this distribution, and that is going to be an estimate of the standard error of the median, right? The standard deviation of the sampling distribution of the median. We could do, for example, quantiles to get confidence interval estimates, and these are the sorts of things that you do with your Bootstrap resample distribution. So let's go through a couple of the principles and just rediscuss bootstrapping generally, and then we'll work through this example a little bit more. So the bootstrap principle is if you have a statistic that estimates some population parameter that you're interested in, but you don't know that statistic's sampling distribution, then the bootstrap principle is simply to use the distribution defined by the observed data to investigate that sampling distribution, an estimate of that sampling distribution. The bootstrap principle actually doesn't require simulation, in the same way that if we want to know what's the distribution of the average of 50 die rolls, well, we could maybe mathematically figure that out. Good luck. But it's easier to do that with simulation. So we never kind of figure out what's the limit of what you get when you roll the die infinitely many times, because we can approximate that so well with Monte Carlo. We're also only going to cover a couple of aspects of what you can do with your Bootstrap resamples. It's a rich subject, and we're mostly going to cover creating a confidence interval and estimating standard errors. So we'll go over those two things. But let's go over the general procedure again. What you do is you take your observed data and you simulate complete data sets by drawing from the observed data with replacement. And this is approximately drawing, and for each of the simulated data sets you calculate the statistic of interest. And this is approximately drawing from the sampling distribution of that statistic, at least as far as the data approximates the real population distribution. So just as a reminder, we're going to calculate the statistic for each simulated data set, and then we're going to use these simulated statistics to either define a confidence interval or to take the standard deviation of this distribution in order to calculate a standard error.
So let's go through the Bootstrap algorithm in a little bit of detail for calculating a confidence interval or Bootstrap standard error for the median from a set of n observations. So the data that we have is a vector of length n. Then what we're going to do is resample n observations with replacement from the observed data to basically get a resampled complete data set. Remember, when you sample from the observed data, you're going to sample with replacement. If you didn't do it with replacement, then you would basically, after having sampled n of them, you would just have a copy of the data set again, just with the order permuted. Instead, it's important to sample with replacement, which means that you likely get some observations repeated on multiple times, which is fine. This is part of Bootstrap resampling. When you get a resampled data set, in our example, we're going to take the median, or if you're using a different statistic, you'll simply take that statistic of the simulated data set. Then you're going to repeat this step over and over. I say B times here, where B is the number of Bootstrap resamples. You want B to be large so that your Monte Carlo error is small. And what I mean by that is, remember, if we could, we would just figure out the exact Bootstrap distribution without involving any resampling. We would just know exactly what the distribution of the median is from a distribution that places probability 1 over n on each observed data point. Instead, we're going to do it via Monte Carlo, this process of resampling, so you don't want the Monte Carlo error, or basically how long you've run your computer, to be driving your results. The easiest way to fix this is to simply make B be fairly large, 10,000 or more simulations. The medians that you get from this process are approximately drawn from the sampling distribution of the median of n observations. We're really sort of approximating the population distribution, but that's okay. There's a lot of theory that shows that the bootstrap actually works. When we do this, what we can do with our bootstrap resamples is the first thing is you always want to draw a density estimate or a histogram of them. But you also could calculate their standard deviation, which will give you a standard error of the median, an estimated standard error of the median. You could take quantiles of your bootstrap resampled medians and say, for example, the 2.5th and 97.5th quantile, and those form a so-called bootstrap confidence interval for the median. So notice what we've done in this process is we've figured out a very easy way to develop a confidence interval for the median without having to do anything like fancy asymptotics. Let's go through some quick example code. Remember the father-son data, where our x is our son's heights. Remember we assigned this vector x to be the son's heights. I'm going to define b to be 10,000. That's going to be my number of bootstrap resamples. And I've already previously defined n as the length of x, the number of observations that I have. So if I want to draw n complete data sets with replacement, b complete data sets with replacement from x, then I need n times b draws. The R command sample does this, where it's x as the vector that I'm sampling from, n times b, the number of times that I want to draw from it, and replace equals true. In this case, if I didn't have replace equal true, it would give me an error because you can't draw n times b elements from x, which only has n elements, without replacement. This now gives me a vector of n times b samples from x. And now I'm going to simply arrange them into a matrix with b rows and n columns. So every row now is a bootstrap resample, and it has n observations. So I'm going to go along the rows in the next line and take the median for each row. When I take my standard deviation of my medians, I get 0.08473. This is an estimated standard error of the median. If we want a confidence interval for the median, I'm going to take my vector of resampled medians, and I'm going to simply take the quantiles, and I want a 95% interval, so I'm going to take the 2.5th and 97.5th quantiles. Gives a fairly tight confidence interval in this case because there's lots and lots of observed data. Here's my histogram of bootstrap resamples, and this is just always a good thing to do. I did it with ggplot, and so here you see me assigning g the output of the ggplot function. ggplot works on data frames, so I define a data frame as my collection of medians, and then my aesthetic, my x variable, is the medians. Then I'm going to add to my plot, I'm going to add a layer that is a histogram. The black means the bars, the outside of the bars are black. Fill being light blue means the inside of the bars I wanted to be light blue. And bin width talks about the width of the bins to create my histogram. Then I type G to actually show the plot. So this plot is an estimate of the sampling distribution of the median. If we had the true population distribution and we were to sample over and over again, this would be a very good estimate up to Monte Carlo error of the sampling distribution of the median. Instead, we don't have the exact population distribution. We've replaced it with the bootstrap principle of resampling from the observed data, and now instead we just get this approximate distribution of this approximate sampling distribution of the median. So a couple final notes on the Bootstrap. The way in which we presented the Bootstrap here is the so-called non-parametric Bootstrap. The confidence interval that I showed you, just taking the 2.5th and 97.5th percentiles, is actually a somewhat poorly performing confidence interval, and you can improve on it very easily. The one I would recommend is called the bias corrected and accelerated interval, BCA interval, and it's very easy to implement in the Bootstrap package in R. You simply take your Bootstrap resamples and pass it through this function, and it just gives you the BCA interval. It's basically a quick little fix of what quantiles you take to correct for a bias. What I've done here is I've just given you a very basic introduction to the Bootstrap. It is an incredibly useful procedure, and it has lots of variations and extremely wide applicability and a lot of intricacies when you try to apply it in settings like when you have time series, or when you have a regression model, or when you have longitudinal or multi-level data. We're going to end the class on something that is an incredibly useful tool for data scientists, so-called permutation tests. And these are used for group comparisons. So let's start with a motivating example of group comparisons where it may not be immediately obvious what to do. So in this example, researchers took batches of insects and applied different pesticides to them, labeled as sprays here. And they counted the number of dead insects in each batch. So for each spray, they got a collection of counts that represented the efficacy of that pesticide. Let's consider looking at insect spray B versus insect spray C. Consider the null hypothesis that the distribution of the observations from each group is the same. In other words, which label a particular count received was irrelevant. So operationally, think about a data frame with the counts down one column and the spray group labels down another column. We would calculate a statistic, such as the difference in the average number of insects killed for group B, and subtract that off from group C. That would be our observed test statistic. Now consider permuting the group labels, just taking that vector of labels and permuting it, for example, with just the command sample in R, which if you give a vector with no arguments, the command sample just randomly permutes the entries. Then you could recalculate the statistic for each permutation. You could use any statistic you'd like. For example, it could be the mean difference in counts between the two groups. It could be the geometric means, or even a t-statistic. You can use a t-statistic and not compare it with a t-null distribution. You could compare it to a permutation-based null distribution. To calculate a p-value, you simply want to calculate the percentage of simulations where the simulated statistic was more extreme in the favor of the alternative than the observed. So more extreme in the difference of means settings would be having a greater difference in the means towards the direction of the alternative. This will yield a permutation-based p-value. Let's go through an example, and I think it'll be much. I'm not going to dwell too much on this slide, but I just want to say that permutation tests are very powerful, and so much so that they keep being reinvented in different settings. For example, the rank sum test, a famous test in statistics, is a permutation test where you've replaced your data in some fashion by ranks rather than the original raw values. Fisher's exact test, which you might have heard of, is exactly a permutation-based test where simply our data type is binary and there's a specific test statistic you're using. If you use the raw data, then you're just doing an ordinary permutation test. I would also add that there's a separate entity called randomization test when you explicitly had randomization, your group labels were randomized. For example, in our insect spray test, batches might have had sprays randomized to them, so it might be considered a randomization test. Operationally, your randomization test is going to be performed in the same way as a permutation test. However, you might have stronger conclusions from your randomization test, and the way in which you interpret your randomization test might be a little bit different. I would also add you can use permutation strategies in regression. So you just simply permute a regressor, and this is a different way to get a null distribution than using the normal distributions that we'll cover in our regression class and as the next part of the specialization. And permutation tests work very well in multivariate settings because you can calculate sort of maximum statistics that control family-wise error rates. We're not going to go over too much of any of this. We simply want you to be able to go through a simple permutation test, get the ideas, so later on you can build on top of this foundation. Let's go through an example where we just illustrate doing permutation tests. First, I'm going to subset the data just so I have insect sprays B and C. My Y is going to be my outcome, the count of dead insects. My group is just going to be group labels, or spray in this case, pesticide in this case. So Y element 1 received is the count of dead insects for insect spray element 1 of the vector group. And the same thing for element 2 of Y and element 2 of group. In other words, my Y and my group vectors are perfectly lined up. So my test statistic is just the average difference, the mean, the average number of dead insects from group B minus the average number of dead insects in group C averaged over batches. My actual observed statistic is just my test stat applied to my outcome and group. Here the two are lined up correctly. Now I'm going to break that lineup by permuting. So now when I apply my test statistic, I'm going to give it my Y, but my group label's permuted. So I'm doing sample group, which permutes my group labels. And I'm going to do that 10,000 times to get 10,000 test statistics where I have broken any association between Y and group by permuting my group labels. This is under the null hypothesis that my group label is unrelated to my outcome. This means that the 13.25 is the difference in the average count of dead insects for B minus dead insects for C, so in excess of 13 dead insects on average killed per batch for B versus C. Let's now calculate the percentage of our permuted test statistics that are larger or more extreme in favor of the alternative than our observed statistic. And it turns out in this data set we get 0. So across 10,000 permutations, we couldn't find a reconfiguration of the group labels that led to a more extreme value of the test statistic than our observed statistic. Or more formally, the p-value is very small, close to 0, and so we reject the null hypothesis for any reasonable level of alpha. I would note the p-value is not exactly 0 because we can think of at least one permutation that is as big as our observed statistic, namely the permutation that gives us back our original data. This is kind of a minor point because we're going to do thousands and thousands of simulations, and whether or not we add that one in or not is kind of irrelevant when we compare our p-value to any normal critical value like 5%. Here I'm showing the null distribution generated by our permutations. Basically, this is serving the same role that our t-distribution or standard z-distribution does in hypothesis testing, where we're willing to assume that either the data is normal or we're appealing to the central limit theorem. We'll see that our null distribution in this case is centered at 0 and goes from -10 to +10. So the fact that we see a -10 means that when we permuted group labels, we saw test statistics as low as -10. What I put here as a vertical line is the observed statistic, and you'll see it's way far out in the tail of our null distribution, suggesting that likely the null distribution is not the correct true distribution, and that B really is very different from C. I think we can just see that from the histogram, but now we can quantify it with a p-value and we can perform a formal hypothesis test. Whether in bootstrapping, where you're looking at the sampling distribution of a statistic, or in permutation testing, where you're looking at a formal inference based on an idea of exchangeability of group labels. In either case, I think it's very important to do these histograms or density estimates to see your resampled distributions.